Welcome back. In this part of the lecture, you will see how to do nonlinear regression based on nonlinear features, based on k-nearest neighbors, and also using kernel regression. In a nonlinear regression, the predicted output is a nonlinear function of the input. You can have, for example, polynomials. So if you take this example where we just have one feature, x1, this can be, for example, again, the size of houses, and you want to predict their prices. Then a polynomial of degree 2 will have this hypothesis function. So you have theta 0 plus theta 1 x1 plus theta 2 x1 squared. You can also define a more complex model by having, for example, polynomial of degree 3. So you will have this hypothesis function. And you can also define more and more complex models by having higher order polynomials. And here are a few examples of nonlinear regression models with two features, x1 and x2. So a second order polynomial in this case will have this hypothesis function. So you have theta 0 plus theta 1 x1 plus theta 2 x2 plus theta 3 x1 x2 plus theta 4 x1 squared plus theta 5 x2 squared. So you have more parameters because we have more features. And if you increase the complexity of your model, for example, by having a third order polynomial, then you will have even more parameters. Let's now see how you can fit a nonlinear regression model to your data just by creating nonlinear features and using what you studied previously in linear regression. Suppose that our original data is two-dimensional. It is described by two features, x1 and x2. And suppose that you want to fit a nonlinear model to your data, for example, a polynomial of degree 2. So you have this hypothesis function, theta 0 plus theta 1 x1 plus theta 2 x2 plus theta 3 x1 x2 plus theta 4 x1 squared plus theta 5 x2 squared. So these are our two original features, x1 and x2. And we can actually consider that this is a new feature that we added, x1 times x2, and we just call it z3. And this is another feature that we added, and it is called z4. And x2 squared is also another feature that we call z5. So our data is now described by 5 features, which are created based on the two original features that we had. And our hypothesis function based on z is just theta 0 plus theta 1 z1 plus theta 2 z2 plus theta 3 z3 plus theta 4 z4 plus theta 5 z5. So this is just theta transpose z. So using our higher dimensional data, we can just find the best values for the parameters using a linear regression model. So this model will be linear in z, but it is a nonlinear model in our original feature space. And to estimate those parameters, you can use exactly what we studied in the previous lecture about linear regression. For example, you can use gradient descent to optimize the mean squared error cost function. And you can actually add any kind of features based on your original features. You can combine the original features in many different ways using what sometimes is called basis functions. But this actually requires a good guess of what are relevant features for your problems. Let's now see how to do nonlinear regression using k-nearest neighbors, or kNN. In kNN, the model is not characterized by a fixed set of parameters theta. So it's a non-parametric model. In the training part, we just save or memorize our training dataset. So we have the inputs x and our outputs y. So this is our training data. We just save it. There is no training as such. And to make a prediction about a new data point x, we first find in our training data the k examples or data points that are the most similar to x, or the closest to x, or the nearest to x. Thus the name k-nearest neighbors. And the predicted output for x is just the average output from these k-nearest neighbors. or sometimes we use the weighted average, as we will see shortly after this. So we need some kind of distance in order to compute the k-nearest neighbors, to find them. Because you need to compute the distance from x to all the data points in your training data, and then take the k examples that are the most closest to x, which means they have the smallest distance to x. And you can use the Euclidean distance to do this. So the Euclidean distance between u and v is defined in this way. Now, given a new input data point x, for which you want to predict the output, and these are the k nearest neighbors to x from our training data, and these are their corresponding outputs, you can just compute the average of these outputs in order to make a prediction for x. And you can also use a weighted average. So you have a weight associated to each of the neighbors, and you just compute a weighted average here. And the weight associated to the ith neighbor is actually the similarity between x and this neighbor. So you have 1 over the distance. So if one of the neighbors of x is very similar to x, it has a very small distance to x, so this weight will be large, and it will contribute more to the prediction. And if one of the neighbors have is very far from x, it has very large distance to x, this similarity will be small, so the weight is small, so it will contribute less to the prediction. And this is the k-nearest neighbors algorithm for regression. So you have a training data set, which has inputs and outputs, and you have a new data point x for which you want to make a prediction. So what you need to do is to compute the distance between x and each of the training examples, right? And then you select the k training examples, which are the closest to x. These are the k examples that have the smallest distance to x. And then you just compute the mean, or the average, or the weighted average of those outputs corresponding to the k nearest neighbors. And that's the prediction, or the predicted output for x. This is just an example where we show, based on example where we have one feature, x1, we show the predicted output using the 5 nearest neighbors. So k is equal to 5 in this case. And the example on the left uses just a simple average. And the example on the right uses a weighted average. So here, the green line shows the prediction corresponding to each possible value of x1. So for each possible value for x1, we make a prediction using the 5 nearest neighbors. And you can see that the weighted k nearest neighbors usually gives a smoother curve here. Instead of using the weighted k nearest neighbors, you can also use something called kernel regression. Kernel regression is very similar to the weighted k nearest neighbors method. One difference is that in kNN you have a hyperparameter k to define the k nearest neighbors, but in kernel regression, instead of doing that, we use all the training examples, all the n training examples in our training data set. Another difference is that, if you remember, in kNN, we defined the weight associated to the ith neighbor as just 1 over the distance between x and this neighbor, the ith neighbor. In kernel regression, instead of doing this, we will use something called a kernel function that gives us the similarity between x and xi. And one kind of kernel function or similarity that we can use is called the Gaussian kernel function, and it is defined in this way. So if you have two vectors u and v, it is computed as the exponential of minus the distance between u and v squared divided by 2 sigma squared. And sigma here is a hyperparameter that you set manually. It defines the width of the Gaussian. So this Gaussian here represents the values of the kernel function with respect to different values of the distance between the two data points. So this distance here. If you have a data point xi in your training data set, which is very close to x, right? So this distance here is very small, it's close to 0, then this similarity or the value of the kernel function will be very high, right? So they are very similar, those two data points. Now, if you have a data point xi which is very far from x, so this distance is very large, right? Then the similarity would be low. This kernel function will give you a low value. Now, if you choose sigma to be very small, then you will have a very narrow function, like for example this one. And so very few data points in your training data set will have a high contribution to this prediction. And if you choose sigma to be larger, for example like this, then you will have a wider Gaussian. And most of the data points in the training data will contribute to this prediction. So you can use such a kernel function instead of the weights of the weighted k-nearest neighbors in order to make a prediction about a given data point x. And here we use all the training examples in our data set, not only the k-nearest neighbors. So just to summarize, we want to make a prediction about a data point x. So we use all our training examples and we use some kernel function, for example, this Gaussian kernel function. And the data points that are closer to x will have a larger influence on the predictions. And you have a hyperparameter sigma that you need to choose. And larger values for sigma implies that more data points will influence the prediction. So very large values of sigma may lead to what we call underfitting, because then you will use all the training data points in your data sets to make the prediction, and you use them to the same degree. They influence the prediction in the same way. But if you choose sigma to be very small, then this may lead to what we call overfitting, because then you will use very few data points, those that are the closest to x, in order to make your prediction. And this is just a comparison between the simple k nearest neighbors. In this case, k is equal to 1, so we have the 1 nearest neighbor, and the kernel regression method. And we do this on a simple example with one feature, x1. And the curve that you see here represents the predictions using the 1 nearest neighbor. So for any value of x1, the predicted value will be the one corresponding to the output of the nearest neighbor, right? So you will get a curve which has jumps. It is not the smooth curve, as you can see here, but the curve that you obtain for kernel regression is smoother. And that's because for any input, we make the prediction using all the training examples in our training data set. So for example, if we have some input data point here, let's call it x, then we compute this predicted value based on all our training examples. But those that are the closest to x will have a larger influence, and those that are a little bit farther will have smaller influence, and so on. Those that are very far will have a much smaller influence on the prediction. We will see later in the course some other methods to do nonlinear regression, for example, when we talk about artificial neural networks.